We are very happy to welcome Frank Vallentin, who is a professor of applied mathematics at Universität zu Köln. In 2003, he received his PhD in mathematics from TU München, and then he was a postdoc at Hebrew University Jerusalem and the Zentrum Wiskunde en Informatica in Amsterdam, and worked as an assistant and associate professor of optimization and system theory at the Delft University of Technology in the Netherlands before coming to Cologne. Professor Vallentin has made several influential contributions at the intersection of optimization, geometry, discrete, and experimental mathematics. Of particular interest to the Codex community is his work on semi-definite programming bounds for packing problems in discrete geometry, including his noteworthy paper, New Upper Bounds for Kissing Numbers from Semi-Definite Programming with Christina Beckhoff, which won the triennial SciAm Activity Group on Optimization Prize. Today, Professor Vallentin will speak on his recent work on the chromatic number of lattices. So take it away.
Okay, thank you. So, first of all, thanks for the kind introduction and the invitation. So I'm happy to give a talk here. So I think it's a great idea to have a seminar across different universities at this time. So let me share my screen in order to start. Okay, good. So you can see my mouse, I hope.
Yes.
Okay, good. So yeah, I want to talk about coloring the Voronoi tessellation of lattices. And this is a joint work with a couple of people, namely with Mathieu Detour, Sikiric, David Mador, and Philippe Boustreau. And we have a paper on archive from last year. And yeah, so in this paper, yeah, we start kind of, we are the first who look at the problem of coloring the Voronoi tessellation of lattices. So it's start-off paper, beginning paper. And yeah, I want to show you some of the results we got, and I want to show you some of the research directions you could go if you like the problem. So first of all, what is the problem about? Yeah, so the problem is, in a sense, we want to generalize the checkerboard. How could you do this? Could you do this? So there are a couple of possibilities. So first of all, you can do backgammon, but then of course you are stuck a bit. You could also go to Brazil, and you have this nice pattern here on the floor. But of course, we are mathematicians, so we like to go from the checkerboard, from the Z2 square lattice. We want to go to the hexagonal lattice, for example, in 2 dimensions. And then we want to color the tiles, not only black and white, but now with 3 different colors, because we want to have that the tiles which are adjacent get different colors. And if you have so many French co-authors, then the choice of colors which are available there is also limited. So this was forced to me by my co-authors. Okay, so now kind of serious mathematics. Now we start with definitions, and then I will explain the problem also by definition, and then I will show you what is known about it and what is still left to prove. Okay, so we want to look at the Voronoi tessellation of lattices. So we have a lattice in R to the n. So a lattice is simply all integer linear combination of some bases. So for example, in this picture here, these black dots in the middle of these cells, they form a lattice. And then the Voronoi tessellation is simply, you take all points, the Voronoi tessellation is respect to the lattice and some lattice vector. And then you take all points which are closer to the lattice point than to all other lattice points. Yeah, so for example, if you take this lattice point here, this one here in the middle, then this white area here is the Voronoi cell of this lattice point, because in the white region, all points are closer to this lattice point compared to all other lattice points. And now you can do this game for all kinds of points, for all lattice points, and then you get this hexagonal triangle. And now the question is, yeah, you want to color this tessellation, and you want to color this tessellation in such a way that two full-dimensional tiles, so two full-dimensional hexagons here, which are adjacent, which share a facet, which share a side here, an edge, they should get different colors. And then you want to minimize the number of colors. So let's be more precise. So let's look at more definitions. So at the end, I want to represent this coloring problem as a graph coloring problem. So I want to I want to define which graph now is behind. And for this, I need the notion of Voronoi vectors. So the Voronoi vector, so it's, I think, easiest to picture it here. So the Voronoi vector is simply all vectors which have the property that the Voronoi cell around the origin, and then the Voronoi cell shifted by the vector, then the intersection between these two Voronoi cells, it's an n-1 dimensional facet. So here in this setting, it's an edge. And in this setting, in two-dimensional space, you see that these 6 vectors around the origin, they form the Voronoi vector. Of course, in high dimensions, these configurations are much more complicated. You have many more vectors. But I hope that the concept is clear. That the Voronoi vectors are simply the vectors which connect the Voronoi cell of the origin to the adjacent one. Now we can define a graph, the Cayley graph. And the Cayley graph is a graph on a group, and the group here is now the group of the lattice. So the lattice itself forms a group together with the plus operation. And then the vertices of this Cayley graph are simply all lattice vectors. And you have edges. You have an edge between two lattice vectors if and only if the difference v minus w is a Voronoi vector. And this means that in this picture, the neighborhood of the origin is consisting out of these 6 Voronoi vectors, and now you copy these 6 Voronoi vectors to all other places, and then you get an infinite graph consisting at the end out of triangles. And that's the Cayley graph. And now the question of finding the chromatic number of the Voronoi tessellation of a lattice boils down to finding the chromatic number of this Cayley graph. So that's our question. We want to determine the chromatic number of this infinite Cayley graph. Any questions about the definition and the problem? Of course, now there are many questions. For example, what is known about it, and what are the first questions we want to answer. And here are the questions. So first question is, what is the chromatic number of some of the interesting lattices? And if you know lattice theory, then it's very clear what an interesting lattice is. I mean, the most interesting lattices are 8 or 24 dimensional because of their relation to sphere packing, because in dimension 8 and 24 it was solved a couple of years ago. And I will show I think with two proofs that the chromatic number of the E8 root lattice is 16, and that the chromatic number of the Leech lattice is 4096. So I will show you this with for the E8 lattice with 2 different proofs, and for the Leech lattice I will show you 1 proof. Another natural question is, what is an algorithm to determine the chromatic number of a given lattice? So I give you a lattice, for example, given by a lattice basis, and then I ask you to determine the chromatic number of this lattice. And can you do this with a finite procedure? And in fact, at the moment, we don't know. So this I want to pose as an open problem. So we don't know at the moment if we can find the chromatic number of any given lattice in finite time. Then other questions. So how fast can the chromatic number grow of a lattice depending on the dimension? And we have two results there. First of all, an upper bound, which is easy to prove, I will show you. And the upper bound is exponential. So the chromatic number can grow at most like 2 to the n. We also have a lower bound, and this comes from the answer to the question, so what is the chromatic number of a random n-dimensional lattice? So on the space of all lattices, you can define a natural measure, and then you can compute the expectation of the chromatic number of a random lattice there. And we could prove that the expected chromatic number of a lattice also grows exponential. And it grows exponential with 2 to the 0.099n. Yeah, there's still a big gap between, of course, lower and upper bound, but nevertheless, it shows that the chromatic number can grow exponentially, and usually grows exponentially in the dimension. Yeah, and in the talk, I want to show you basically proofs of all these results. And but before that, I want to dig a bit deeper into the Voronoi vectors, because we need some structural properties of those. So again, the Voronoi vector is a vector having the property that the Voronoi cell around 0 intersecting the Voronoi cell around the vector is an n-1 dimensional facet. And then there's a beautiful characterization due to Voronoi, how these Voronoi vectors look like. And these Voronoi vectors are exactly those vectors where plus or minus u is the only shortest vector in the coset u plus 2 times the lattice. And I think it's easiest to see this and to understand the theorem from this picture. For example, I want to show you that this vector u is not a Voronoi vector. Yeah? It's clear because the hyperplane orthogonal to u doesn't define a facet, so it just defines a vertex here. And this is now easy to see from the theorem of Voronoi. It's also easy to prove because if you look at the coset of this vector u with respect to lambda, then you see that, for example, this vector u lies inside, this vector here lies in the same coset, this vector lies in the same coset, and this vector. So all vectors where you have a red area around it, except for the middle one. And you also see that you have 4 different vectors which all have the same length, and you cannot be shorter than that. So the theorem of Voronoi shows that u is not a Voronoi vector. And the proof is basically like this. I mean, u is not the only shortest vector in its coset. So there's another shortest vector in the coset, which is not u or minus u, like v. Okay. What else? Yeah, then you just take the average, a half u plus v. And this you can prove gives you a shorter vector by some simple computation. It's shorter than u and shorter than v. And it defines, in fact, a facet. Usually, if you take the average of 2 lattice vectors, then you don't lie in the lattice because you take a half here. But now, because u and v lie in the same coset mod 2 lambda, this vector now lies in the lattice. And this picture basically illustrates the theorem of Voronoi, but also basically gives you a proof of the statement. Yeah, it also shows that the number of Voronoi vectors is finite, because they are at most the number of different cosets, and the number of different cosets is 2 to the n minus 1, because you exclude the 0. And this gives us also immediately upper bounds for the chromatic number. So if you take a course in graph theory 101, then you know that by an argument by greedy coloring, you know that if you have a finite graph, then the chromatic number is upper bounded by the maximal vertex degree plus 1. You just color the graph greedily. And this we just apply to 2 lambda periodic colorings. Now we look at 2 lambda periodic colorings. So now the finite graph is lambda mod 2 lambda, and then you have edges whenever the corresponding lattice vectors differ by a Voronoi vector. And then it's clear that this chromatic number of the lattice is upper bounded by the chromatic number of this finite graph, because we just look at 2 lambda periodic colorings. Then by the greedy coloring, this is upper bounded by the vertex degree plus 1. And what is the vertex degree here? The vertex degree is simply the number of Voronoi vectors divided by 2. And the number of Voronoi vectors is upper bounded by 2 times 2 to the n minus 1, because 2 to the n minus 1 are the number of different cosets. And we multiply it by 2 because we have plus u minus u in the coset. And then this gives an upper bound of 2 to the n. In fact, in most cases, or in many cases, this is less because not every coset gives you a Voronoi vector. So in fact, this is a sharper upper bound. So this gives an answer to one of the questions. So what is the number of colors needed at most? And it's most exponentially, and this comes from this easy upper bound. Of course, in coloring, lower bounds are much harder to get. And I want to show you 2 different methods how to find lower bounds. The first method comes from sphere packing, and the second method comes from the spectral bound, kind of related to, if you like, semi-definite programming, but this is very much hidden. So, okay. So first of all, I want to look at sphere packing bounds. And here's a theorem which will help to prove, for example, the chromatic number of E8 and the chromatic number of the Leech lattice, as well as the chromatic number of an expected random, the expected chromatic number of the random lattice. Okay, so here's a theorem. So we have a lattice, and this lattice should determine a packing of unit spheres. So we want to center at every lattice point a unit sphere, and we want to have that this is a packing. So we have to scale maybe the lattice, but scaling the lattice doesn't change the chromatic number. Then we want to have a number mu, a positive number mu, so that whenever I have a lattice vector, non-zero, which has norm strictly less than mu, then this should force V to be a Voronoi vector. We already saw that Voronoi vectors are short vectors by the characterization of Voronoi, but now I want to give a global bound on the length of Voronoi vectors. And this is mu. And if I have this mu, then I immediately have a lower bound for the chromatic number. And the lower bound is as follows. The lower bound for the chromatic number of lambda is mu divided by 2 to the power n times delta of lambda. So that's the center density of lambda. So the number of lattice points per unit volume divided by delta of Rn. And delta of Rn is the largest sphere packing density in Rn. So the lower bound is determined by mu, by this global bound on the length of Voronoi vectors, and then this is a fraction comparing the center density to the optimal sphere packing density. And of course, this bound is good when these 2 when this fraction is small. And the fraction cannot be better than 1. And if it's 1, we have a situation when the center density coincides with the larger sphere packing density. So this already gives a hint why this bound could be good if you have a lattice with optimal density. Okay, so the proof is easy, and every math talk has to contain a proof, so here it is. So suppose the chromatic number of the lattice is k. Then we can decompose the lattice into color classes, C1 up to Ck. And then now we assume that the first color class has the largest center density. We assume that k times the center density of C1 is greater or equal to the center density of the entire lattice. But for example, which you can get when C1 is the color class of the largest density. Okay, then we know that if you take excuse me. So if you take two lattice vectors in C1, which are different, then the difference between V and W is at least mu. Because the difference is never a Voronoi vector, and when you don't have a Voronoi vector, by the assumption, the difference should be at least mu. So that means that we can scale C1 by 2 divided by mu to get a packing of unit spheres. Yeah, so the color class C1 scaled by 2 divided by mu defines a packing of unit spheres. And then we plug in kind of the usual estimate. So if we have a packing of unit spheres, and this packing of unit spheres cannot be in density larger than the largest sphere packing density. So then we have k times delta of Rn is greater than k times delta of the scaled color class. And this is greater or equal than mu divided by 2 to the n times the center density of lambda, because C1 was the color class having the largest density. And now you shuffle things around, and you get the lower bound for k. Yeah, so that's an easy argument, but nevertheless it's quite powerful. For example, we can apply it to the E8 lattice, and we can apply it to the Leech lattice. Yeah, for the E8 lattice, we know that the optimal center density of packings in R8 comes from the E8 lattice. It's kind of by the famous breakthrough result by Marina Wiazowska from 2017. And in the same way, by another breakthrough result by Kohn, Kuma, Miller, Radchenko, Wiazowska, also from 2017, we know that the optimal sphere packing density, dimension 24, comes as a center density of the Leech lattice. And if you plug things in to the formula, you get a lower bound of 16 and 4096 for E8 and number 24. And then it's not too hard to also find a coloring, having 16 colors for E8 and having a coloring with 4096 colors for lambda 24. Yeah, so this solves the coloring problem in these two cases, but of course using heavily the result by Wiazowska et al. Yeah, then we can also apply this theorem to generic lattices. And before we can do that, we need a lemma. And this lemma says how big the mu is. And the lemma is an easy geometric lemma, says that whenever I have a lattice defining a packing of unit spheres, and V should be not a Voronoi vector and not 0, then the length of V is at least square root of 8. Okay, and then we plug in the square root of 8 from U for a generic n-dimensional lattice. Then we get this estimate over here. And so we need now an estimate for the center density of lambda. And this is given by the Minkowski-Lafka lower bound. If you have a random lattice, then the Minkowski-Lafka bound gives you a lower bound for the center density. And we need an upper bound for the sphere packing density in Rn. And this is given by the optimal known or best known upper bound by Kabatiansky and Levenstein. So these are two exponential numbers, exponential in n. And if you plug in everything at the end, you get this exponential lower bound of 2 to the 0.0990n. Also coming from this rather easy sphere packing argument. And the real work again is not by us, it's done by Minkowski-Lafka and by Kabatiansky-Levenstein. Okay, good. So this solves the coloring problem for E8 and number 24. Now we have a second bound, the spectral bound, for getting lower bounds for the chromatic number. And this is basically coming from graph theory 201, so second course of graph theory. And then you would learn the Hoffman bound. So the Hoffman bound is a bound, lower bound for the chromatic number for regular graphs. So you have a finite R-regular graph. And then the chromatic number is lower bounded by 1 minus 1 divided by little m of A. So now I need to define what A is, and I have to define what little m is. So first of all, A, what is A? A is the normalized adjacency operator of the graph. So basically, it is an adjacency matrix of the graph and normalized by the fact that we divide everything by R. So it's a matrix where all the entries are either 0 or 1 divided by R. And it's 1 divided by R at the positions where you have an edge. And if you want to write it down into matrix vector terms, then the matrix vector multiplication is simply doing this. So if you want to evaluate AF at V, you are sitting like here, you're sitting at the vertex V, and then you average your function F over all the adjacent vertices. Okay, so that's the normalized adjacency operator. This is A. And that little m of A is simply the smallest eigenvalue of A. Or in optimization terms, it's minimizing the Rayleigh quotient, or it's minimizing the inner product between AF and F over all vectors F having the midlength. And once you have your matrix A, and once you have found the smallest eigenvalue, you automatically have a lower bound for the chromatic number. Usually this lower bound can be improved by doing some optimization, so you can optimize over all weighted normalized adjacency operators. Then you would talk about the lower theta number. But in some cases, especially if the graph has nice transitive group actions, this optimization wouldn't yield anything new. And that's also the case in our application. Then in some work with Christine Bachoc, Evan de Corte, Fernando Oliveira, we saw that this doesn't only work for finite graphs, this also works for infinite graphs if you just make the right definitions. And in our setting, instead of working with matrices and normalized adjacency matrices, we work with, operators. Operators, mapping small L2 of lambda to small L2 of lambda. And they basically do the same thing. So you average, as here, you average your function f over all the neighbors of the graph. And you do it normalized, so you divide by the number of neighbors. So in our setting, it's 1 divided by the number of Voronoi vectors. Then you sum over all the Voronoi vectors, all the neighbors of f of v minus u. And f itself should be elements lying in L2 of lambda. And then basically the same statement, the same theorem holds true. So So the only difference now is that in this setting, maybe you don't have eigenvalues anymore. You simply have, yeah, this minimization problem. And maybe you don't have the minimum anymore, but still you have the minimum. Okay, so now we want to find the lower bound, 1 minus 1 divided by m of a. And to do so, in our setting, we apply some Fourier transformation. Because, I mean, it's easy to see that the adjacency operator is a convolution operator. So it's a convolution operator with respect to the characteristic function of the Voronoi vectors. Yeah, so if you go, we go back one slide, you see here immediately that you have a convolution operator with a characteristic function of the Voronoi vectors. And that's nice because yeah, convolution operators are easily diagonalized by the Fourier transform. Because the Fourier transform diagonalizes A. So instead of computing the inner product AFF, we can also compute the inner product in Fourier space. So AF hat, F hat. And so at the end, the only thing we have to do is we have to look at the Fourier transform of the characteristic vector of the Voronoi vectors. And this is simply this trigonometric sum. So we have this trigonometric sum, the sum of all Voronoi vectors of e to the 2 pi I, here's an I missing, u times x. And now this is a function on Rn mod the dual lattice. So the dual lattice are all points in Rn, so that the inner product between any lattice point in y is an integer. And to compute the Hoffman bound in our setting here, it's sufficient to compute 1 minus the infimum over this trigonometric sum. And of course to the power minus 1. So what we have to do is now to find this minimum of this trigonometric sum. And yeah, so we saw this bound, and then we thought, well, let's try to use it in some settings. And we wanted to use it for the root lattices, because that's maybe the second nice class of lattices after E8 and the Leech lattice. And of course, E8 is a root lattice itself. So what is a root lattice? Yeah, a root lattice is a lattice where you have a couple of properties. First of all inner products between lattice points should be in Z. Then the length squared should be an even integer. And we also want to have that the roots, so these are all vectors of norm square root of 2, they generate number. Yeah, so these are the 3 properties defining a root lattice. And the nice thing about a root lattice is that if you have a root lattice, then the Voronoi vectors coincide with the roots. So coincide with all the vectors having squared norm equal to 2. And it's a very classical result of WIT that these root lattices can be classified. So every root lattice is an orthogonal direct sum of irreducible root lattices. And these irreducible root lattices are AN, DN, E6, E7, or E8. So they come with these famous Cochran-Duncan diagrams for irreducible root lattices. So you have a graph AN and graph DN, E6, E7, E8 here. And you have to make an interpretation like this, that every node of the graph corresponds to a basis vector. Then basis vectors are connected in this graph if the inner product is equal to -1, and if they're not connected, then things are orthogonal to each other. Yeah. And these diagrams now encode all the root lattices. And now we thought, well, maybe it's nice to find out what the chromatic number of these root lattices are, and it's also maybe nice to find out what's the Hoffman bound in this infinite setting gives for lower bounds for the chromatic number. Yeah, the first observation is that if you have a direct orthogonal sum of lattices, then the chromatic number is the maximum of the components. I mean, that's useful because the root lattices are direct orthogonal sums of the reducible ones. So it's nice to see, yeah, that we can compute the chromatic number once we understand the chromatic number of the reducible lattices. There's a small proof, but I think I want to skip it. And now it's the task to find out, yeah, what the chromatic number of these root lattices is and what the lower bound of Hoffman is. So let's do it case by case and see if something interesting comes out. So first case an is defined like this. It has n times n plus 1 roots. They're given by these vectors here. Not so important maybe. And then the theorem we could prove is that the infimum of the trigonometric sum, so the sum over all the roots of an, is equal to minus n plus 1. So that's a little, yeah, at most half-page computation. And once we have this infimum computed, we can also have a bound, a lower bound for the chromatic number of an, and it's at least n plus 1. And then it's also easy to show that the chromatic number of an is less or equal to n plus 1. So this lower bound, together with the matching upper bound, completely now solves the chromatic number problem for the an lattices. So nothing really surprising comes up here. So Dn is more interesting. So Dn is the next class of irreducible root lattices. So here you have a bit more roots. You have 2 times n minus 1 roots. They are depicted like here. Then we could also prove a theorem finding the infimum of the trigonometric sum, summing over all the roots of Dn. So the proof is a bit more complicated, especially because it's a case distinction. So it's minus 2n if n is even, and it's minus 2 times n minus 1 if n is odd. And then if you translate it back to the lower bound of Hoffman, we show that the chromatic number of Dn is at least n for even n, and it's at least n plus 1 for odd n. One can also show that the chromatic number of Dn is at most n, if n is a power of 2. But in general, we don't have an exact value for the chromatic number of Dn, and that's related to the chromatic number problem of some other finite graph. So we can show that the chromatic number of Dn is the chromatic number of the half cube, but in fact this is an open problem in combinatorics. So we don't have a closed formula for the chromatic number of Dn for all n. So I will show this at the end of the talk. But nevertheless, so not so much interesting things here happened. Then E8. Okay, for E8 we already have a proof for the chromatic number, but still we want to compute the lower bound by Hoffman. Then E8 can be constructed also using coding theory, using construction A. So that's coming from the extended Hamming code, H8. So the extended Hamming code is the code of the 16 binary vectors. And then construction A is a construction how to get E8 from this Hamming code. So these are all pre-images of the mod 2 reduction. So whenever you have a vector mod 2 which lies in H8 and you take the pre-image, you scale it appropriately by 1 divided by square root of 2, you get E8. And from this you also see the Voronoi vectors. So there are 16 vectors of the form plus minus square root of 2 times the standard unit vector EI, and then you have 2 to the 4 times 14 vectors coming from Hamming code vectors of weight 4. So these vectors here in the middle they determine basically up to signs the Voronoi vectors. And then we try to compute the infimum of the trigonometric sum. And then we got stuck for quite some time, a couple of weeks actually. And then somebody of my co-authors, they found some Oberwolfach report by Seher, by accident somehow. And this Oberwolfach report is a 2 or 3 pages report, and it contains theorem 3 prime. So one has inf x in G, trace of a joint representation of x is equal to this one. Then we could observe that what's computed here was basically exactly the trigonometric sum we were interested in. So the trace of the adjoint representation as x is n plus the trigonometric sum we wanted to compute. And then Seher computed this infimum for a couple of groups, also now related to root lattices. So he has more Coxeter-Lincoln types because he was looking at groups, not at lattices, but especially he computed things for AN, for DN, for E8, E7, and E6. And it's interesting to say what he says about the proofs. And he says the proofs, so they are not published yet. And here are some hints for the interested reader. And the case which is interesting to us is kind of the last couple of lines. So the opposite inequality here can be checked by case-by-case explicit computation. The classical groups like AN and DN are easy enough. Okay, that's exactly what we could do on half a page. But F4, E6, and E7 and E8 are not. Especially E6, which I owe to another field by the winner, Alan Kohn, and I hope there is a better proof. Okay, so now we understood slowly why we got stuck, because 2 field medalists worked hard on this and they were not satisfied with the proof. So one of my co-authors, David Mador, he was hunting Seher down at some Bourbaki seminar, and he asked for a proof. So Seher was very kind and he explained the proof to him. It was a 10 pages, more or less hardcore computation, which we also included in an appendix for our paper. Then we were not completely satisfied, and then we were trying to work a bit harder to find better proofs. And in fact, we got an alternative sum of square proof for the E8 case, as well as an alternative proof for E7 and E6. And it works along the following lines. So the spectral bound, again, is 1 minus the infimum of the trigonometric sum to the power minus 1. Then we plug in exactly these Voronoi vectors using construction A. And then the statement is that the spectral bound is equal to 16 for E8 if and only if this following polynomial in 8 variables, degree 4, is non-negative on the cube, on the 8-dimensional unit cube having side lengths 2, minus 1, plus 1 to the 8. So the only thing we have to check at the end is that this polynomial is non-negative on the cube. And for this, optimization helped us. So we were able to do this by computer verification. So we could write down this polynomial using sum of square techniques. So we could prove that P of t has a representation as Qt, where Qt is the sum of squares. So it lies in the cone of 8 variables, degree 8, sum of squares, plus multiplier 1 minus ti squared. This comes because we want to have that the polynomial is only non-negative on the cube, times qi, and qi is another sum of squares. Okay, so this is an alternative proof of Seher's result. And this works for E8 in a similar way, and a bit simpler it works for E7. And in fact, for E6, we have another proof which works basically along the same lines, but it doesn't use any computer computations. But also working using techniques for optimization. So E6, E7, E8, they different like here, and then the theorem is that we could reprove what Sarah was doing, that the infimum of the trigonometric sum is -9 for n is equal to 6, it's -14 when n is equal to 7, and -16 when n is equal to 8, giving us lower bound for the lattice, the chromatic number of the lattice E6, E7, and E8. And in fact, the chromatic number of E6 and E8 is tight. So it's 9 here and 16 there. So 16 is now the second proof of the result. And for E7, the chromatic number is off. So here's a summary. Here are the reducible root lattices. Here are the spectral lower bounds. Here are the exact values. And for E7, the lower bound is a bit off. It's 10 and the exact value is 14. So to get the exact value of 14, we had to use another computer program. So we used the SAC solver. So we found an optimal coloring with 14 colors there. Good. And then the chromatic number of the root lattices Pn is open. So our bound n and n plus 1 is not always tight, but we could prove that the chromatic number of this vertex of the Dn lattice is a vertex edge graph of the half cube. So we take the convex hull of all vertices of the cube, where the sum of coordinates is even. And in fact, it's an open problem, I think, starting from dimension, 11 on what the chromatic number here is. But that's part of extremal combinatorics. So we're not specialists there. So we were thinking we did our jobs, and this is now left to other people. Good. I think that's everything I wanted to talk about. Here are some references. If you want to see more details and more results, thank you for listening.
Yeah, thank you very much. Does anyone have any questions? All right, I have